and its integration with ROS to you guys. And it's my first time that I'll be representing aerial robotics community here as of now. A little about myself. I am Tejal. I am just graduated out of my undergrad from IIT Bombay, Mumbai. I'm currently doing a day job with New Space Research, where I work on quad rotors for the Indian Army, and we actually have just delivered some of them during the conflicts that were conducted in previous few days between India and Pakistan. So I'm proud to say that I was part of that product. I'm naturally a tinkerer at heart with a good amount of interest in robotics research and enthusiasm to actually contribute to open source. About how did I actually become a part of aerial robotics community? It actually goes back to my undergrad days, where I was working with a couple of my seniors to actually solve a student challenge, where we had to actually go through a couple of obstacle course with a quad rotor. So we were facing this issues where quad rotor used to run inside dead ends, and we had to solve this. And we came up with a really good approach for second year sophomore at that time, where we used to actually tackle these dead ends using something called as a yaw survey that we used to do at different levels, and we used to tackle it that way. So that is how I got into aerial robotics. And yeah, till now, I think the most exciting subfield that I'm interested in is aerial robotics. So I'm really excited to begin this presentation. So I shall get started. Uh, I think a few minutes ago, I shared a file, a tar file in the in the chat. I request you to please keep it on download, because it's a huge file and it will take some time to download. Till then, we'll continue with our presentation. I'll be happy if someone could give me an acknowledgement with respect to this. Yeah. Yeah. Okay. So we shall move with the presentation then. So before going into how a drone works into SITL, HITL, PX4, Ardupilot, let's go over to have a drone system overview. How does a drone system work? So let's start with the heart of the drone system. We have the flight control unit. This flight control unit has basically a hardware aspect of it and a software aspect of it. So the hardware aspect, as you can see, is here as an example, is a Cube Orange, which is a very vastly used FCU in like among the entire world. This particular board that you see here has a couple of sensors like barometer to measure pressure, so that you can get an estimate of the altitude at which you're flying. You also have accelerometers, gyroscope, magnetometer, and compass inside it. And you have redundancies in those systems as well. So you can have multiple IMUs. So this is the hardware aspect of it. While we come to software, you have different autopilot softwares running on the system, which basically use these sensors to actually estimate the position of the vehicle and then command motors to actually fly, the motor PWM to actually hover over, move to a position, etc. This particular flight control unit gets also interfaced with a lot of other sensors to augment the position estimation system. It could be an optical flow sensor, or it could be a GPS as well. So with all these, you also interface your flight control unit with the telemetry radio. So what does telemetry radio do? It basically helps you to actually have some communication with the drone that is flying in the air and with the laptop that you have on the ground. So the laptop that we have on the ground is generally called as a ground control station. It could be just a laptop through which, with a software called as QGC, you can just monitor the behavior of the drone, or it could be a full-fledged radio control system where you also get a joystick to actually give commands to the drone and fly it basically. So telemetry radio on the drone helps you to actually communicate with the vehicle status and monitor it. Then to augment the computing capabilities that are there on the FCU. So basically, the compute unit that you have on FCU is just a simple microcontroller. It doesn't have much capability to process images, to process point cloud, and do some really cool autonomous behaviors. So for that, what we do is we interface this FCU with a companion computer, generally a Jetson Xavier, Jetson Orin NX, or could be RB5 as well, and you interface this particular companion computer with other sensors that you have. It could be a camera, it could be a lidar, it could be any other sensor, like maybe a laser rangefinder itself. And all of this together makes a drone system over. So given now you have an idea about a drone system, let's go briefly over the autopilot softwares that are available that you flash on the microcontroller present on the flight control unit. Also, free feel to interrupt me somewhere if you feel that I skipped something or you have a doubt in mind. So in terms of software autopilots, we have PX4 and Ardupilot. They basically have a very similar functionality, a very, very similar functionality. The only difference lies is the community support and the licensing that they provide. PX4 provides you with a BSD license, which means you can use it, you can modify it, and just go ahead with it. Ardupilot, on the other hand, wants you to contribute the changes that you have made on the autopilot that you have worked with. So it basically like holds your hands to not use it for any commercial purposes if you're changing it completely. Ardupilot is more in the industrial use because Ardupilot has a lot of partner companies in Australia, in US, and in Europe. So they get more of an industrial support with the Ardupilot developers themselves. With PX4, it is more like a hobby community. It has more features, which are some of them are very experimental, but it is more user friendly, I would say, to get started with just. So today we'll be focusing on Ardupilot because like I prefer Ardupilot because it has a more stable control systems, like a slightly different from PX4, very slightly different. So it gives a more stable output for the drone control. So before we move on to experimenting with Ardupilot and stuff, let's go over with ROS2. Like ROS2 is in like craze right now. So why is that? So basically, ROS2 provides you with an optimized format of ROS1 and like helps you to communicate faster, helps you to tweak the communication parameters also to a really good extent. So because we are flying drones at a really high altitude and at some really far distances, like 14, 15 kilometers, the communication link itself becomes very critical. So we can't afford to have very heavy packets being transferred from the drone to the laptop that is at the ground control station. So that is where ROS2 optimizes for it. And also there are some other benefits as well because now the entire community is shifting to ROS2 and we have lots of commercial backing, some certifiability, new middlewares coming up. So yeah, ROS2 is the way to go because it will accelerate your development for mapping and planning and also like give you a lot of community support going forward. So now I'll explain you how does Ardupilot ROS2 SITL interface actually works out. So SITL is basically a software in the loop simulation. It's basically a virtual way to fly your drones. So you can change your autopilot software, you can change your algorithms on the companion computer, and you can still test out all the experiments that you want to do it without risking the hardware, which gives you a lot of added benefit because a lot of times don't crash and we lost our resources. And that is where SITL comes into a really helpful tool, a really, really helpful tool. So at this point of time, I've created a demo to actually work with SITL. So like as a reminder, I would request you all to actually click on that drive and install the star file because this will be very, very useful for the experiments that we'll be doing ahead with ROS2 and Ardupilot simulation. Okay. So coming to here. So SITL, as it says, it's simulation in the loop kind of a setup. So what it does is basically you have Ardupilot ka autopilot software running on the microcontroller that is on the FCO. This microcontroller ka software, which is called as Autopilot, has a library called as AP underscore DDS library. So what it does this AP underscore DDS library is basically an interface which is converting Autopilot Maverick messages into something which is compatible with DDS. DDS, as we all know, is the middleware that is used by ROS2. Now think about this. DDS as a middleware is a very heavyweight implementation of packing in, encapsulating all the ROS messages, all the packets that you have. How can we implement this DDS on a microcontroller? So that is where micro ROS agent comes into picture. Micro ROS agent communicates via protocol known as micro XRCE DDS. XRCE stands for resource constraint uh, it stands for Resource Constraint DDS version, which basically is a very lightweight implementation of DDS. So what it does is basically a micro ROS agent is being run on the Ardupilot side. This Ardupilot side gets a server. Now, when you create ROS2 nodes on the companion computer, there are several clients created. These clients actually communicate to the server present on the microcontroller via micro XRC DDS protocol. And therefore, this micro XRC DDS library becomes a lot of important. We'll see this again when we go over on the tar file tutorial that we have. Following this, we have the math proxy GCS. So like normally you have some user-based software running with you called as QGC through which you can control drone, monitor drone. But for the SITL, we have a special software called as math proxy. Math proxy is basically a console-based interface for GCS, which allows you to interact with the drone in real time with some terminal-like commands that you can perform, and you also can monitor the drone using that. So we'll be going through it now. So I'll be skimming through all of these instructions that Ardupilot developers have provided just to give you an idea about how you can install the system if you want to do it on a native system. I've currently given a Docker file which has already been set up for all the SITL simulations that we need. But if you want to do it on a native system, this will help you a lot. So first of all, it starts with, it wants you to install ROS2 Humble, and they prefer Gazebo Harmonic over Gazebo Garden. So that's fun. Then they start going on to installing Ardupilot repo itself, building it, compiling it, and then they go on to installing MicroXRC DDS Gen to maintain consistency between hardware setup and software setup. This micro XRC DTS agent is also used on SITL setup so that it is easier for developers to transfer their code from sim to real environments. So they have given the setup installations. It is pretty much very easy to follow and it works out of the box. And finally, you just Qualcomm build all the ROS2 packages involved in the system and you're up and running. I really hope that everyone has downloaded the tar file. Hello?
Yes, some of us have downloaded it.
Not everybody.
Yeah.
But come
on. Shall we wait for everyone to download it?
Yeah, I think you can still go ahead. So for those of us that have already downloaded it, we will move on. But for others, they will have to just follow along.
Great. Okay. So first of all, the place where you have downloaded the tar file, you can just load the tar file using this command that I've shared in the presentation in the chat. I'll share the command again in the Teams chat. So using this, you can basically load the tar file into a Docker image. Uh, I hope if everyone can do it. Please
Yeah,
feel
can you
free
come again?
to. Yeah. I have put up a command on the chat to actually load the tar file. So, like, if you can use that command to load the tar file, it would load a Docker image onto your system. Like, once you're done with using that command, just let me know. Wait for some time; it will take some time to load, but don't control C it. Like, don't cancel the process. It will take some time to load.
Yeah. All right. So I think what we're going to do is, since it will take some time, you can just continue. By the way, this meeting is being recorded, so whoever wants to go ahead and implement some of these things, they always have to. You can just go over the video, so you can just keep on, and then we'll take
I
notes.
think that's awesome. That's awesome.
Okay. So you can load the tar file using it. Once you have loaded the tar file, you can use Docker image list to actually see if that image is appearing. So once you have loaded a tar file, it would come as basic Ardupilot tutorial with a tag v1 on it. So this is how you would be able to see if the image has been loaded. Once you see that the image has been loaded, now let's start running it. This particular image has basically been built on the installation Docker that was given by the Ardupilot. I have run all of these instructions along with the Ubuntu installation instructions that they have given with Ardupilot 4.5.7, which is the latest firmware that we have right now for Ardupilot. So yeah, let's run it. For every command that I run, I'll be providing some description of why are we running this command. So the second command that you see here is basically providing the Docker container that we are going to run with the permission of using the display of my native system to actually export the math proxy console that we are going to see now. So now the connections have been added to the access control list. Now we can start running the Docker container. So now you can see that the Docker container is run because now I'm inside the root of the Docker container list. Here you see there are things like ROS entry point.sh, ddsgen.sh, and if you go inside the root folder, you will exactly find the audio underscore workspace that we saw here inside the tutorial. It's exactly the same. So once you go inside that, you will have the install, everything is already built inside here, so you don't have to build it. Now we are going to actually source this workspace to you start using the ROS2 nodes that we have for SITL. So go hover on the ROS2 with SITL link. This particular tutorial is actually just about launching the SITL with the micro ROS agent and ensuring that you can run a particular GCS called as MapProxy for it to control the tone. So you'll be able to control the tone. You'll be able to see it on the map and see ROS2 interfaces to actually command it also and get position estimated data from it also. So we have already sourced this particular workspace. Now we are going to run this command. So if you see, this particular command has a lot of arguments, like it has UDP ports, it has some configurations related to DDS as well. So this basically helps us to know what ports are we launching for the drone so that we can bind to it, so that our GCS can know on what port, on what communication protocol is we have to communicate it to, and what other copter parameters. Like there are many copter parameters, and as we'll see now, in the tutorial, which you can tune to make the control to make the drone more agile, or maybe the way you want it to control. Maybe it can be related to the position controller itself. It can be related to how you want to have the attitude control configured. It is all inside this particular command that we are going to run. So all the parameters are loaded inside this particular command. So now if you see, it is loading the firmware, it is loading key. Okay, this is a quad rotor that we are going to run. There is an EKF, extended Kalman filter running, which is using some IMU0. There are redundancy, as I mentioned before. So there's also IMU1 in the system. There are magnetometers, which is helping it to align yaw with the system. Currently in simulator, they also try to simulate GPS and flight battery as well. Flight battery, but always remains at 100%. They don't reduce it, but they reliably can simulate GPS very well. So based on where you want to actually simulate the drone as well, you can provide that argument to the drone. So you can launch it in Australia, you can launch it in India, wherever you want. So I'll be going ahead and opening one more terminal in this particular container, which you can do it using the docker exec command. So this will just open one more terminal inside the same container. So now we are inside the same container. So this guy knows that, okay.
Sorry, please. Are you sharing the screen for the new container you just opened now?
Yeah, I'm sharing my entire screen, my entire laptop screen.
Okay, because I can see the screen is splitted into two. One is for the slides,
Right.
right? And then the
Right.
other screen is for the terminal, right?
Yeah, and the terminal screen is also split into two. So you have two terminals open here.
Okay, so from my own end, I can only see one terminal screen. I don't know if others are having the same
I can
issue.
see the two terminal screens. I can see the two terminal screens.
Okay, you can see the two. Oh, maybe it's my issue then. It's the issue is from me. All right, you can move on. You can move. Thank you.
Okay. So now we have one more terminal open inside the same container. I'm going to do the same thing. I'm going to hop on to the audio workspace that we had created, and I'm going to source it. So now that we have sourced it, we have run through all these installations that we had to do. We can now go ahead and use this command to actually ROS to launch Ardupilot SITL that I've already done in the terminal one. So this basically gives you access to a lot of ROS2 node stuff through which you are communicating to the autopilot. So now that I've sourced here, when I do ROS2 node list, I should be able to see Ardupilot underscore DDS. So basically, this is the Ardupilot underscore DDS that we see, which is getting the data from the autopilot and communicating it to ROS2. So let's see what all data does it have. So I'm gonna just do ROS2 topic list here. So we see there's Autopilot battery percentage, there's a clock, there's a GPS position, there is a facility to command velocities, there is some geopose filtered, navsat 0, pose filtered, and see. Let's skip some part of it and hop on to the map proxy part so that let's start a particular GCS so that we can take off the drone and move it around a bit, and then we'll come back to this ROS2 interface later. So as soon as I ran math proxy, you saw here two consoles open. One is basically giving data about what is the status of math proxy, what is the status of drone. It says that mode is stabilized and stuff. What copter version are we running? So we are running firmware 4.5.7. What is the frame and the flight battery? Here you see a map overview of the system. So now let's go ahead and take off the drone. So in the slides, I have also attached basically a screenshot of the math proxy helpful commands that you can use. So there are commands like takeoff, there's a mode that you can change, there's parameter you can change, you can change, you can tell it to go to a particular position, you can give a reboot command, you can arm it, a lot of things that you can do. So we'll be using today some of these commands to actually control the drone, and you'll see how does it help us. So in Ardupilot, to give you a very brief overview of all the modes that we have here, we have something called as stabilize, which is basically a pilot has full control over the altitude, over the position in X, position in Y, attitude of roll, pitch, yaw, everything. There are other modes called as loiter. Loiter, still the pilot is commanding, but the pilot doesn't have control over attitude, but only position of the drone. In case there is one more mode, so which our companion computer particularly talks to it and can command the drone, and that is called as guided mode. So in guided mode, we can use it, you can use our companion computer to talk to the FCU and control it completely. So we are gonna take off the drone here in guided mode itself. So as you can see here in the screenshot, if you want to change the mode, you can specify mode and the mode that you want to change it to. So if I want to change it to mode guided, I'll just type mode and just guide it. So this will help us to change the mode from stabilized to guided mode, which means now the drone can accept the guided mode commands. Just to help you how you can use this is always you can type dash dash help in front of the command that you want to use, and it will give you the things that you can run, basically all the commands that you can run. So now we have changed it to guided mode, we are going to arm the drone first. Arming the drone is just basically spinning the rotors, spinning the propellers on the ground itself. And when we push the takeoff command, the FCU basically gives a throttle to the drone equal to the weight of the drone. And then it starts going up, dhire dhire, slowly. So yeah, now that we have changed the mode to guided, we are going to do arm throttle. So this will just arm the drone. So we see that the motors have been armed. If I take off the drone, let's say particular takeoff altitude of 10 meters, it says got command acknowledgement and the takeoff has been completed. So now the takeoff has been accepted. So if you see now here, we don't have the 3D view, but what we can do is we have a better way to actually note down the position of the code. So we can again execute into one more terminal inside the container, go hop into the audio workspace, and see the ROS2 topic list. ROS2 topic that gives us the position of the drone. If you see here, there are a lot of interfaces that you have. So let's say we go on to AP post filtered. So what this does is this will give you a position estimate of the drone from where it took off. So if it took off at 0,0,0, the position that we should see right now should be 0,0,10. So let's see if we are going to see that. So now you can see the position is 0, 0, and 10 meters. So it took off to 10 meters basically. So this is one of the interfaces that you can use. To follow more on math proxy, you can give it position commands as well. It could be just as simple as position 10, 0, 0, and the drone will start moving forward. If you see here, we'll give it a bigger position, let's say 50, and you'll see it can go ahead. The other thing that you can do is you can also use your mouse click on this particular map to actually command a flight to location and give it altitude as well. Let's say I give it an altitude of 10 meters. So my drone will start going towards there. So you can use it this way as well. Okay. So this basically gives you an overview of the SITL. Now let's come to ROS2 part of it in a more detailed manner. So okay, our drone reached the position that we commanded it to go. So let's hop on to all the ROS2 interfaces, all the ROS2 topics that we saw a couple of minutes ago. There are so many interfaces that it provides you, right? So what are these interfaces? So these interfaces have been documented by the Ardupilot developers in a tabular format here. As you can see, you can get the IMU data as well, airspeed data, like if you want to get position estimates, attitude estimates, you get all of it here. You also get time interfacing, like if you want to have the time of the companion computer be synced with the time of the FCU for whatever reason. It might be that you have some, maybe let's say, lidar inertial odometry algorithm running on your companion computer. Now you want to send this post data to the FCU to merge it with the EKF running on board. Then how do you do it? You want to ensure that the messages that you're sending from the companion computer to the FCU are actually time synced so that autopilot can merge those messages appropriately. So for that, we have these messages so that we can do that time sync part. We have control over also. So currently we can control the global position, basically command latitude, longitude, and altitude to the drone. We also have an interface to command directly velocities to the drone using this particular message. And you have some services also through which you can arm the motors, take off the motors and stuff. So you can explore all of these by doing ROS2 service list and all of those. Today we'll be going over one particular example of basically actually commanding the copter with a velocity command today. So before going on to that, let's explore what is this APCMD well about. Okay, so we see that it has a type of geometric messages, twist stamped. The other thing that we want to see is, okay, so specifically I typed in verbose here. Basically, I wanted to see what is the QoS profile of this particular message. There is a compatibility check between QoS profile messages that can talk to each other. A transient local message cannot talk to a best effort message. So we have to ensure that we are having the same compatibility between these guys. So to do that, what I've done is I've entered a QoS profile of sensor data as well, and I've added a description of geometric messages as well, where I am commanding a velocity of 1 in X direction, but in the frame ID of base length. So this would be in the body frame that we are commanding a velocity of 1 meters per second. So the drone will start moving in its heading direction with 1 meters per second का value. So let's hop over and use this command to actually command the drone. So you see that the drone has started moving forward in this particular direction slightly. I'll increase the velocity to make it more visible. Let's say I'll start moving at 6 meters per second. Sorry. Yeah. So the drone will move faster now with 6 meters per second ka value, but in the heading direction. So this is how you can command the velocities in the base link frame, that is in the body frame. If I change the velocity to actually just y direction, it would start moving laterally. Yeah, okay. Uh, After, because this is done, this is what I wanted to cover with respect to basic SITL simulation. Now we'll move on to some other roster interfaces and more examples that we have. Yeah. So this is basically a goal interface for Waypoint roster. This is how you can command roster. Uh, I have covered CMD well command. This particular tutorial covers the part to actually command a global position itself, where you command a latitude, longitude, and altitude to the system in one particular coordinate frame. And this is where GPS also comes into picture, because without GPS, there's no relevance of latitude, longitude, and altitude, because it's a global position source. So using this command, because this is already being documented, I'm not covering here in this particular video session. You can explore this later in your free time. Uh, there's one thing more that I wanted to cover. So as you go here, after this comes a ROS2 with SITL Gazebo setup, which is running approximately everything same that we ran until now, but it's also launching the Gazebo simulator. That's the meaning. So there are a couple of other setup instructions that they have provided. I couldn't provide this all of the setup instructions in the Docker image itself. So I would encourage you to install this on your native PC and try it. It is going to be really fun. And to just show you how it looks like and how it comes up, I'll go ahead and run this particular simulation they have given. Uh, so I'll stop this particular simulation first. Exit the container. So I'll be going over to my roster workspace and I'll be sourcing the entire workspace. Now I'm ready to run this particular simulation. So as you see, this particular simulation comes up with a gimbal as well, which is rotating, and it provides all of the with the TF3s and stuff, and with the iris quad rotor that is simulated in the RVIS. You see the same quad rotor over here, which is there for the Gazebo simulation setup, and a very similar map proxy things that we saw, that the codex is being loaded, the EKF3 library is being loaded, and what IMU it is using, what is the GPS and stuff. So in a very similar manner, I'm going to run with the map proxy stuff, the same command we used. So yeah. So this gives us a very similar interface that we saw, but along with it, now we have Gazebo as well. So here, when I actually load the mode guided and arm it and take it off to, let's say, just 2 meters for now. So the quad rotor takes off and moves, hovers to 2 meters. We can always use the same command that we ran for the velocity control, and the drone will start moving. Hello.
Okay, I wanted to ask.
Uh,
Hello, Teja. Hello, Teja.
yeah. Was I
Okay.
interrupted in between?
So I think personally, I didn't hear your voice for a while, so I wanted to know if you were still on. Yes.
Uh, like I'm sorry, I received that my Teams was not able to connect. Like what part did I miss? If somebody could, I'll share my screen again.
Oh, you can share your screen again. Yes.
Can you see my screen?
Yes.
Yes.
Okay. Like I wanted to ensure like what part uh from which part did I actually went away from the video call? Uh,
Oh,
was this visible when I actually commanded the drone with some velocity data?
I think when you started the map processing node.
Oh, okay. Uh,
Yes.
okay. I'll go over and send it. So I'll start it from where I left it off. So now we have the map proxy started, where I've changed it to guided mode. In a very similar way, we did it for the Docker session. We armed it and took it off to 2 meters of altitude. So now the drone is flying at 2 meters of altitude. The same command that we actually used to actually control the drone in the Docker setup, we can also use it here to command a drone with some velocities of 1 meters per second. So this way the drone will start moving at 1 meters per second. So now that we have seen the same velocity simulation, we can like look into other things as well. So I talked about there are a lot of parameters that you can use and tweak the drone ka behavior and stuff, right? So all of these parameters are actually available with something called as param. So with param, you can see all the parameters that you want to have and set those parameters as well. So let's say if I type param and with the help, it will show that you can have param fetch, you can param save in a text file, you can show some param as well. So let's hover and see some param. So let's say I gave it a param of param show WP speed. So we have WP nav speed up, we have WP nav speed down, we have WP nav speed. So let's say we just see WP nav speed. So we see that this WP nav speed is set to 1000. This 1000 is actually in centimeters per second, so it is set to 10 meters per second, which means if you command the drone to go here with some velocity and tell it to fly, let's say 2 meters per second, 2 meters of altitude. And while it goes there, if you start monitoring the speed of the drone, so you see that speed is approximately 7 in X and 7 in Y. And if you calculate the magnitude of the speed, it would come around 10 meters per second. So it is moving 10 meters per second in the horizontal direction. So what if I change this particular parameter? If I change this parameter to, let's say, param set WP nav speed to, let's say, just 2 meters per second. So that is 200 centimeters per second. So I can show the parameter to actually confirm that it has been set it to that value. Now, to actually load this parameter, you have to first land the drone and then you have to arm it again. So it will load that parameter completely for your next flight that you do. So I'll switch the mode to land and this will enable the drone to land at a particular horizontal position that it's at currently. So we can see it's landing inside the Gazebo simulator. So now that it has landed, you can arm it again, switching to guided mode. And take off to 2 meters. Okay, I'm not sure why the takeoff is failing. I'll start the simulator again and it will load the parameter. Also, I forgot to mention, unless you have the 3D position fixed, you cannot arm the drone. So because it says pre-arm need position estimate, until and unless the GPS is being fused, you can't arm the drone.
Hello, sorry, please. Can you mute yourself if you're not the speaker? Please mute yourself if you are not the speaker. All right, sorry,
Okay, so,
Tejal, you can go ahead.
yeah, so now that we see that EKF3 is fusing IMU with GPS, now we can start doing the arming of the drone. So now the takeoff command has been accepted. We see that the drone has took off. So now we can again command it someplace here to go. Now that it's going, we can monitor the velocity, and now you see the velocity is really small. It's just 1.73 and 0.9 meters per second. So speed might around be 2 meters per second, just because we had set the WPNAV speed parameter to just 2 meters per second. So it is following that. So this is where you can alter the behavior of the drone based on what you want to do. So this is one part of it. With this, you can move ahead with to some advanced tutorials, which due to time constraints I won't be following in this particular, but I've documented it all. So there's this project that I had created. I'll show you the video first of all. So it basically uses the same exact simulator, but in a different world. So on the Gazebo, on the Ardupilot documentation page, you have many other worlds called as a maze world, and you can add different sensors as well. So this particular simulation that I'm showing you right now has a lidar sensor on top of it, and the iris turtle has been spawned inside the maze world, if you see that. So this is how I have created a particular map, and the all the tutorials and all the installation process with the libraries that I've used to create this map, I've documented it very nicely in a particular repo here. So this ensures all the dependencies you want has been installed on your system to run this particular thing with the instructions to also launch this kind of a simulation. So basically, if you see here, yeah, you have different world. You have iris underscore maze, you have runway, and you have wild thumper also. So that simulation that I just saw, which was using iris underscore maze, and this is a tutorial that follows to actually run that particular simulation, so which you can create a good mapping world, which in which you can do obstacle avoidance. It has also been included in this particular repo itself, so you can try that out as well. So yeah, that's it, I think, from my side. Hello.
Thank you very
Am I
much.
audible?
Yes, yeah,
Yes,
audible.
you're
Thank you
very
very much,
audible.
Teja. Thank you very much, Teja. Very wonderful presentation as regards the Ardupilot and drone development. So right now, we'll be opening the floor for questions. This is a great presentation. We'll be opening the floor for questions. I think someone's hand has been raised, and if there's a question also on the chat here. So I'll say like there are two questions on ground. If there are more will be coming in. So we'll be opening the floor for questions. So I want Murwa, sorry if I pronounce it wrongly. Okay, to go ahead with question. Yeah. So after him, I'm going to take the question on the chat here. So Murwa can go ahead with question. Hello.
Yeah, go ahead.
And okay, while we are waiting for him, I'm going to take the question on the chat here. Also, to make it easy for those that have questions, if you can put it on the chat, just in case your network is not very good, I'll put it on the chat so it's easy to maybe pass it through. Yeah. So I'm going to take the question here. He said to obtain the relative or local coordinates, would it be possible to set up a base station in the area where the drone is being launched? So that's the question from Clean. To obtain
Uh,
relative or local coordinates, would it be possible to set up a base station in the area where the drone is launched?
yes, definitely. So basically, when you have a GPS on board with the barometer, you have the home location where you actually armed the drone from, launched the drone from, and that particular location becomes your home position. So if you see inside the ROS2 topic list also, you'll always get two topics about the position of the drone. You'll get one topic which basically lists you with the global position of the drone, which is geopose filtered, which gives you latitude, longitude, altitude in the global sense. And there is also this AP pose filtered, which is basically the global pose that you had from the geopose filtered, like, and offsetted from the home position. So this acts as a local position source for you then, because this is always with respect to the home position, the place where you launched it from. I hope that answered your question.
Yes. Sorry, I don't know if you understand me very well. Hello.
Uh, Hello. Yeah, I can
Okay.
understand you.
Okay. That is my question. The question about the local, the relative position is my question. I want to continue, Jos. I want to know what is the precision of the local position. If
Right.
yes, what is the precision? Just sorry for my
Right.
English.
So, if you are using GPS, your local position accuracy is relatively not so precise. It has a precision of about 1 to 2 meters, 1 to 2 meters, which is not very precise. If you want to go for more precise methods, I would encourage you to look into visual inertial odometry, lidar inertial odometry, and that is why one of the biggest reasons why people still use these things over GPS is because it gives you access to GPS denied areas, and it gives you a more precise local position as well from the place that you launch, given you have enough features in your environment. So GPS gives you an accuracy of about 1 to 2 meters max. But with respect to using lidar inertial odometry and visual inertial odometry, given they have been configured properly, you can get up to centimeter level accuracy with them.
Okay,
Does that
thank you.
answer your question? Yeah.
Thank you very much for that answer, Teja. Great work. So generally LiDAR visual odometry are better for good precision and accuracy as over GPS. Yeah, thank you very much. So there's this other question. Actually, there's a question that's looking at that is Davis wants to know the advantages between using the PX4 over the Ardupilot firmware.
Right. So, based on what amount of PX4 and Autopilot I have used, I believe PX4 gives you a lot of support with respect to get you started on. You have lesser parameters to configure. You have more support with respect to when you want to introduce some external navigation system. Let's say if you want to fuse some output of other odometry source, radar inertial odometry, for example, with the Autopilot position estimate, then I still think PX4 has an upper hand over it because it gives you a lot of interfaces. Like you can, for example, time sync the IMU that is present on the onboard flight controller unit with the LiDAR sensor that you have that is connected with the companion computer. So it gives you these experimental features. But Ardupilot, on the other hand, is a very like old release, but it gives you a very good stable controls of the system, like very stable controls with respect to PX4. Now PX4 is also catching up, and these two are like just as alternative, and it's based on the user preference on what they want to go with. But if you want to develop more like experiment more as a hobbyist, or if you want to change a lot of the flight controller code itself, I would prefer going with PX4 just because PX4 has more readability in the code insights as well, so it's easy to understand and change it, modify it, experiment with it. With Ardupilot it's not so easy, but it has more stable performance, as one can say.
Yeah, thank you very much, Teja. I don't know if that question was answered well, Davis. I don't know if it has been
Yeah, it was
answered
okay.
well.
Yeah,
Yeah.
it's okay. It's okay. Yeah, I got it.
So more if you are looking for something more stable for your project and you want to use maybe PX for Ardupilot, just go for the Ardupilot. But if you like to think around, you can go for the PS4 as an hobbyist. Yeah. So I think I'll go to the next question now. That's Lewis Ajagun. So he wants to know how we can really get into this. We want to know how we can start the Ardupilot or the drone, this whole stuff, Ardupilot PX4. As a beginner, what's your advice for someone that wants to go into this as a beginner? What's your advice? Yeah, so that's the question.
Okay, so like a couple of people from SITL Robotics community have compiled a really great list of resources. I'll share that in the chat later, which has like a lot of resources to get started on to understand the drone dynamics itself, and then hopping on to setting up autopilots and then using them, understand them more, and then using them for simulation and hardware purposes. So I think that would be a great resource to get started on with. But I would recommend to actually first understand the system itself. How does a quad work? How does the position is controlled? How does yaw is being controlled? How they're controlled based on motor commands. That's the first thing you would want to understand. And then you can start moving on to using these autopilots in ROS2 and Gazebo simulator that would provide you with a lot of context about what is going on, and help you to control drone in a lot of ways, and then going forward with that. I'll share those resources in a while in the chat.
Okay, thank you very much. Thank you very much. So please, you'll be sharing a description in the chat for those that want to start newly. So I'll try and pick some other questions because of our time, so we can meet up with the time. So I just want to there's a question. Okay, there are two questions. Said, can I use a companion computer like Raspberry Pi alone instead of using Pixhawk or both flight control and AI? So I
Yeah.
think the question is about, can you just use just a Raspberry Pi instead of bringing flight control and the companion computer. So that's just the question.
Okay. So yeah, definitely you can use the companion computer Raspberry Pi alone instead of the ready available FCUs that you get. But with just that Raspberry Pi, you have to write all of those control algorithms to actually command motor PWNs and then get data from external sensors called as IMU, barometer, integrate them to use them as a position estimate source. So all the software that is onto the flight controller unit, if that can be implemented on the Raspberry Pi, then you can definitely go ahead with just using Raspberry Pi as your source. And I believe a lot of people do it as well. Like I think Model AI does it to some extent, where they have flight controller and estimation software on the RB5, Qualcomm RB5 itself, and they just use the onboard computer to go ahead with it. So yeah, that can be done definitely.
Yeah, thank you
Uh,
very much. Okay. So thank you very much. So I think for that question, I think Mr. Joshua, I think you are is quite clear for the question. So if you can build it on your own from scratch, you can teach the controller. So, but he also asked the question. He wanted to know. You talked about using ROS for long range communication. But he
uh,
wanted to know if telemetry could. Why can't telemetry just handle that, or do you have anything to just add to that?
uh, like I would say, like telemetry does handle it to some extent. Like there are protocols such as other protocols such as which are more lightweight than ROS2 itself, like SMIC. But there are interfaces which helps you convert ROS2 to SMIC and then you transfer data. But in between the process also that you have going inside the OBC and the autopilot, because let's say if I have a attitude control running on board my OBC, like onboard computer, and I want to communicate to the autopilot, then ROS2 again gives me an edge over ROS1 to communicate it with much better controls over how I am communicating. The messages, the queuing size, the history that I'm keeping, all of that control is more. I agree with long range communication, it does like fade out a bit because we have other protocols as well. Because ROS2 again, it's getting converted into some other protocol to get it converted and send it out to the ground control station, but it still is better choice than ROS1 as of now.
Okay,
I
thank
think
you.
like I'll be getting back to this particular question again in the chat.
Good. That I think that will also be good. Yeah, thank you very much for that answer. So for more answers, like Dejal said, she'll be getting back also maybe during as the meeting progress during in the chat. So because of our time, I'll just going to take one more question. We have just less than 5 minutes. I'm just going to take one more question before we round up this section. I want to take a question from Mulwa. I think he raised up his hand earlier, so I want to just take a question from. Okay, I think maybe one of his question was answered. Okay, he wanted to know if you want to test the drone indoor. He wanted to know would optical flow sensor work well for guided mode? Maybe testing the drone indoor. Would optical
Okay.
flow sensor work well in guided mode? Yeah.
Yes. So we have experience working with arc flow, optical flow sensor. So optical flow sensors, generally good optical flow sensors come with their own IMU and distance sensor with a small camera also, which the distance sensor actually ranges from 10 meters to 30 meters based on its range. So these particular optical flow sensors, which I have worked with, can give up to good velocity estimates up till 10 meters per altitude. They can't help you to actually hover at one point because at the end of the day, it's an optical flow sensor. So it expects that the drone would be moving. It expects the environment is static, and because the drone is moving, the pixels, there is some pixel movement happening in the picture. So at 10 meters, around at 10 meters, it can give you a good velocity estimate, but the hovering still is very, very bad. You'll see the drone doing a motion called as toilet bowling continuously at also 10 meters. So for indoor flight, it can work up to a certain extent as long as you're moving continuously, but for hovering, not so much. So yeah,
Okay. Yeah, thank you
and yes,
very
it
much.
will work well with guided mode as well, like
Okay.
up to 10 meters.
Thank you very much, Teja, for that answer. I believe that question was well handled here. Thank you. Thank you very much. I can see the thumbs up. Thank you very much, Teja. Because there's a lot of questions here. So I want to know this
Uh,
question. I just want to ask this
sorry,
question so that
quick
we can round
question.
up. Sir?
Sorry, I have a question.
Oh,
Yeah,
okay.
Should I go ahead?
yeah, please.
Oh, oh, okay. Elisha Abi. Is that Elisha?
No,
Or...
this is Security Salau, Lekon, Security
Oh,
Salau.
Mr. Sikri. Okay, so go ahead, sir.
Oh, all right. So, I think some years ago, I actually used the software in the loop, but it was I used it for ROS1, the Ardupilot ROS1 software in the loop. And one of the issues I had, so I want to know whether it's still an issue or not. So that time I wanted to simulate like 100 drones because we are doing a kind of algorithm like a particle swarm filter, like a kind of like sorry, we call it a lot of birds trying to flock together. So that kind of
Okay.
simulation. You might have like maybe 100 drones just for that. But if you know, because I noticed something when you were presenting, and it's that when you want to run, which was like similar issue we had that time too, if you want to run the SITL, the software in the loop, it's like you need to have like 4 terminals to be able to run just one drone.
Right.
You have like 4 terminals running. And I could remember because I wanted to run 100 drones. So I wrote a shell script that's tried to run 100 drones. So it's more like as if you want to do 100 times 4 terminals. That's 400 terminals running at the same time. So is this still an issue if you want to run multiple drones? Do you have to run like four terminals for each of the drones?
No, actually, now Ardupilot and PX4 have come up with their own launch files where you can run multiple drones. I'm not sure if they support 100 drones at a time, but definitely multiple drones are available to be taken off at the same time. The other way at my company, how we are handling this is actually we have created a Docker environment where the Docker itself we have configured for one particular drone, and that configuration is very reproducible. And we are running each of those Docker images as a separate, simulating it as a separate computer entity in itself. So that we just run that Docker YAML file, the compose file, and it basically runs the entire 4 drones that we want to simulate at the same time. That is one way to go ahead with it, but I'm pretty sure now PX4 definitely, and Ardupilot also for ROS2 version, they have created a launch file where you can launch multiple drones at the same time in the same simulation setup. So I think you can look into that.
All right, thank you.
Yeah, thank you very much, Teja, for your answers to the question. And like I said earlier, there's a lot of questions for you, so much questions for you. What I just want to ask, so that we can go to the next presentation. Maybe, like you said, since you said you answer some of the question on the chat, I want to know if is there a community that people can join for the area robotics, so maybe they can get more answers or things like that. Because there's a lot of questions people have here as regards this.
Yeah, sure. So in the Open Robotics Discord channel itself, there is a channel for the aerial robotics community where anyone and everyone can join it and post questions for whatever doubts they have. We also have different Discord platforms for Ardupilot and PX4, where you can also put in a lot of your doubts and get them cleared, and people will be very happy to answer. So I'll be sharing all those 3 links as well in the chat with the resources, and I'll be going over the entire chat to answer the questions.
Yeah, thank you very much for the wonderful presentation. Please, can we just give a round of applause to Teja? Please, can we give a round? Let's react with a round of applause. If you really value this speech, yeah. Thank you very much once again, Teja. We'll be expecting some of your answers and also the link to the community where others can join, maybe to get more info about the area robotics, the Ardupilot, and the rest with ROS. So thank you once again, Teja. Thank you very much. Yeah.
Yeah. Thank you so much.
Okay. So we are going on with the meeting. We have another presenter. His name is Tosin Oseni. I think I met him at the first ROS meetup in Nigeria where we had in Lagos. I think that should be February, I think 2023. Yeah, and he's an AI. He's an artificial intelligence person. He's a researcher, and he's going to introduce himself properly as he's going to be presenting. So I'll be bringing on Tosin, Mr. Tosin Oseni. You are welcome. Let's give him a round of applause. Yeah, you are welcome, Mr. Tosin. Yeah.
Hello, everyone. Sorry. Hi, my name is Tosin. I want to apologize because it's 6 a.m. here, so I'm still very much asleep. Yeah, so like you said, my name is Tosin. I left to the US to start my PhD in robotics. I'm attending a university called Colorado School of Mines, a small research university in Golden, Colorado. And I'll be presenting on kind of my research work. It won't be it might not be as fun as Teja's presentation. There's not going to be raw stuff there. Let's talk about research. And if anyone finds anything cool, you can ask me questions. Can everyone see my slides? Okay, thank you. Right, so I'm going to be talking on robot exploration, inspection, and dive. This is an old talk I gave in my lab, so I'm just going to give the same talk again. How do I? About me, I'm a first-year robotics student, like I said, PhD student. I'm advised by Dr. Michael Cora. He's in the computer science department, but I am a robotics student. My undergrad was in mechanical engineering in Nigeria, called Kobna University. I'm more of a researcher than an engineer, although I do have undergrads that work with me that they take on the engineering role for me. My research areas are in RL, visual SLAM, robot inspection and exploration, and robot learning. But most of the work I do with my advisor is on the robot inspection and exploration. What is robot exploration, right? So if you have some kind of unknown area like a mine or someone's audio is there. If you have some unknown areas, whose audio is that?
Sorry, please. If you are not speaking, if you are not the speaker, please try to mute yourself, please. Thank you.
Yeah, thank you. So what is robot exploration, right? You have some unknown area you haven't been to, like a mine or a factory, and you want to drop a robot into that space, and the robot needs to like autonomously explore that area. So some of the reasons why you do that is if it's too dangerous for humans, like space, volcanoes, minefield. So we're trying to figure out how do we build robots that can autonomously explore this area. So like I said, it's just too dangerous for humans to explore, or you want to perform something called autonomous mapping, whereas you drop a robot, but you don't want to manually drive the robot around. And there are two kinds of exploration. There's task agnostic and task oriented. So task agnostic might be, you just want to explore the entire area. I don't really care about anything specific. Whereas task oriented is you want to maybe find an artifact. You want to find cracks in a mine or unsafe places. So in task agnostic, you don't really need to reason about the problem, except maybe like closure loops. I don't know how familiar people are with Slam, but you want to perform loop closure sometimes because you get a more accurate map. So that's the only reason that you have to do when it's task agnostic. But when it's task oriented, you need to reason about the problem you're trying to solve. For example, if you're trying to look for a cup in a house, you wouldn't go looking for a cup in a bathroom. So you'd go, say, looking for that in a kitchen or in a bedroom. So some of the work we're trying to do at our lab is building agents that can reason about this exploration problem. So what is robot inspection? Kind of similar to exploration, except you aren't like searching an entire space. You have some kind of artifact or structure you're trying to inspect, and you want to like say maybe get the temperature reading or fracture reading from the artifact. So it has really a lot of applications in industry, a lot of applications in manufacturing, whereas you typically use a human being. So we're trying to figure out how would you automate this with robots.
Please, if your speaker is
please
on,
let
please
me
can you
mute his mic.
Oh my
I
god,
think-
that just made me miss Nigeria. Oh my god, that's insane. Okay, so like, what are the class of problems we're trying to solve? Like I said, robot exploration, reason about the exploration problem, semantic mapping. I'll talk about that real quick. 3D reconstruction in relation to robot inspection. Why do we need to perform 3D reconstruction? Simulation and why it's important to my work, current progress, next steps, and required technologies. So the class of problems I'm going to be working on specifically is in an industrial setting, we have a set of goals, which might be an embedding, can be a text description of, okay, we need a generator, or we need, a factory or some, we need a certain tool to be looked at. So it could be text, it could be image inputs. And we feed this to this algorithm / robots. We want the robot to navigate this complex environment and to return back with information about the goal we provided to the agent. So if it's the first time the robot has been to that factory or environment, it needs to perform exploration. So that means it needs to go around and actually look for these artifacts, like I said. But if it's not, and we give the agent the map, he knows exactly where to go to, and all he has to do is perform inspection. So what is semantic mapping? Semantic mapping is a mapping framework where we don't just have some geometric understanding of the world, we have some contextual understanding of the world. So we could like label, this is a room, and then the room would have like a chair, and then the chair could have like a cup on it. So we have some kind of hierarchical reasoning of the environment. And this sort of map representation allows us to perform exploration tasks easily or efficiently. 3D reconstruction. I'm sorry, like I said, this is just a bunch of like different modules from my research that I have to bring together. So luckily PhD is like 5 to 6 years, so I have time to figure all of these out. 3D reconstruction. So in typical fashion, a human being would go out and perform the inspection tasks themselves. Whereas 3D reconstruction, the agent would perform, take pictures of the artifacts. The pictures have to be like good enough quality so that we can perform 3D reconstruction. And when we have 3D reconstruction, a human being can now sit down and then look at the reconstructed image. So why is this relevant to inspection? Like I said, if it is high fidelity enough, if it is clean enough, it is good enough, the rendering is good enough, then we can always go back in time and, you know, inspect the artifact ourselves. So, so why do we need to reason about 3D reconstruction? You know, like if I give an artifact, why can't you just take pictures of every single object, every single side of this thing, of the artifact? Because all pixels are not created the same. So like if you have a fracture of like your artifacts, you know, you have some cracks, those pixels might be more important than some random blob in the artifacts. So we might want to care about some images more than others. We might want to zoom some areas more than others. So that means that we can't just take pictures of the artifact. We need to plan about how we take pictures of these things during the 3D reconstruction. So some other aspects you need to worry about is safety in some regions. Like in a factory, it might be dangerous for you to put a robot here. So the robot might have to find a safe angle to take pictures from. You might not want to ruin the people that are working. You might not want to take their time. So you might want to, again, take the picture from somewhere else. So that means you need to plan your trajectory. You need to reason about the trajectory. You need to reason about where you want to, if you want to zoom, if you want to pan, you know. So those are the complexities that come with 3D reconstruction. There's this thing called Gaussian splatting. I don't know if anyone knows about it. 3D Gaussian splatting. Wish I could show a picture. I'm not sure. A video. Yeah, so you can all look this up later on. This looks really good. This is high fidelity. Gaussian splatting is a reconstruction algorithm where it would represent, you know how in robotics you have like voxels or point cloud. Gaussian splatting represents the world as 3D blobs or 3D Gaussians more specifically. So it's incredibly fast, it's incredibly accurate and high fidelity. And when 3D Gaussian splatting was released, I think 2 years ago, it blew the competition out of the way. So this is a technique that was adopted in the lab just because, like I said, because of its advantages like speed and high fidelity. Reinforcement learning and simulation. So I've spoken about exploration tasks, I've spoken about inspection tasks, what they are, but how do we actually perform the reasoning about it? How do we build AI agents that can actually think about the problem? So back home in Nigeria, I had started my research in reinforcement learning, and that was how I was able to get a PhD here. So reinforcement learning is a branch of machine learning, which is not so popular anyways. I mean, it is now, but it's a branch of machine learning where you train an agent to perform a task. You do that by awarding rewards to the task you're trying to solve. So it means that we need to define some kind of reward function that would explain, or rather that would kind of, how do I explain this? We need to define some kind of reward function that would define how good an exploration task would look like, or define how good an inspection task would look like. So learning methods have been shown to have significant progresses in the last few years, as opposed to like handcrafted heuristics. A very good example of this is like ChatGPT, Cloud.ai. So the what they call them, the chatbots now are like significantly way stronger than chatbots from a decade ago. So we need to define reward function for exploration. So that could be, okay, if you've explored this area enough, I'll give you a reward function. Or we use this very complex reward functions called information theoretic reward functions. So like Shannon entropy, or mutual information. I don't want to go into all of those things. So yeah. So those are the reward functions that you define for exploration. So you could say, if you cover this much area, I'll give you a reward. Or if you have a map of the world before, and then you say, okay, if you've explored it, then I compare the map of a fully explored world to the map you got, I could define what a reward function will look like. However, inspection is much more difficult, because how do you define what a good inspection looks like? So the easiest way to do this is to compare the object we've reconstructed to some kind of rendering of the object. But you can't really do that in real world. So a very simple solution to that is to use a simulation like NVIDIA Sim, or there's one that comes with ROS. It's called Gazebo. So if we can compare the reconstruction we made to the 3D world itself in a simulation, we can have a realistic comparison between the two. However, in our lab, we don't use Gazebo, or we decided not to use Gazebo because we felt the rendering wasn't clean enough. So we use a software called Isaac Sim and Isaac Lab, which is incredibly very strong. I would advise you not to run it on your laptop or it will fry. Just kidding. So, like I said, a realistic simulation allows us to go back in time and then compare the, if we have a simulation of it, we have some kind of oracle, and we can compare the image we took to the actual image in the simulation, because you just have to perform, rendering in that direction. So the required systems we need for my research is a realistic physics simulation, like I said, Isaac Labs, Isaac Sim, a mapping system for navigation and exploration. So we need some SLAM systems running in the background. We need 3D reconstruction from Gaussian splatting, a robot with high maneuverability and required sensor suite. So 3D camera, 3D lidar, Husky observer. I want to mention that my lab is kind of new. So we've been doing a lot of purchases and stuff for robots, lidars, sensors in general. After, you need a module for learning and running neural networks. So the robot we are working with is a Husky observer, which is basically a Husky with extra money, because it charges so much for the extra sensors that put on top. But it's specifically made for the inspection and exploration task. It comes with these sensors, sensors, PT zoom camera. So PT zoom camera is kind of like a regular camera. It's kind of big, but it lets you it has really strong configurations for panning, tilting, and zoom. Hence the PTZ. Microphone, optical, thermal cameras, and then you have the regular sensors like 3D sensors, lidar sensors, depth cameras, GPS, yada yada. So the next step in my research is, once we started up the simulation, like I said, we had to buy a new computer because Trump ruined all the tariffs and stuff. So it was difficult to buy a new computer. We had to wait for everything to die down. Integration with ROS and mapping setup, and integration with reinforcement learning libraries. So yeah, sorry the presentation was short, and I'll now be taking questions. So feel free to ask me original questions, career questions, research questions, and why I decided to do a PhD and stuff like that. So you guys are free. I'm done, by the way.
All right, I think Samuel is going to take it from here. Let's wait for Samuel. Samuel, are you there? Hello, Samuel. All right, so I think I can hear Samuel. So let me just take it up from here then. If he comes back, he might just have to take over from me as well. So we have some questions here.
Hello?
Yeah, okay, Samuel is here.
Hello,
Samuel,
can you hear me?
are you here? Oh, yeah.
Yes, I can
hear
hear
you now. All right, go ahead, Samuel, please.
Okay. Okay, thank you very much.
I can't hear Samuel. I don't know if I'm the only one.
Yeah, I can't hear him either.
Okay, Samuel, we cannot hear you. So because of time, let me just take it over from here. And if there is, if you are good with your audio, then you can come back. All right, so we have some questions here. I think somebody raised hand. Okay, we have like 2 people raising hands now. All right, so the question here is how does, this is from Davis, how does Gaussian splatting compare to traditional SLAM, or compared to the traditional SLAM-based mapping approaches in terms of accuracy and completeness? Okay, Tosin.
That's a very good question, actually. Gaussian splatting is not SLAM algorithm. It's a novel view synthesis algorithm. So it means like, if I were to give you a bunch of images, can you create some kind of 3D rendering of it without? And then the reason why it's called novel view synthesis is because you don't have access to every single pixel. So like, if I were to just take some pictures of my screen right now, I'm not going to take a picture of every single angle. So the algorithm is to figure out, okay, yeah, I don't have an exact pixel of this position, so I'm going to kind of make it up, right? So that's what Gaussian splatting is. It's also similar to NERF. However, after Gaussian splatting dropped, the SLAM community or the visual SLAM community all flocked into producing Gaussian splatting SLAM algorithms, which would do the same thing more accurately with completeness, but the world itself will be represented with Gaussians. So, and it would look better. It looks better. It looks more cleaner than other algorithms. So that's what it is. So Gaussian splatting itself is the novel synthesis algorithm, which is different from SLAM. So it would not be accurate. Yeah, it would make up the pixels on spot, hence the well view.
All right. Thank you for that. We'll move to the next one. I think, if I'm correct, Sugaba, is that the name? You can go ahead with your question,
Yes.
please.
The name is Sugaba. Can you hear me?
Yeah, I can hear you, Sugaba.
All right.
Yeah.
Thanks for the presentation. Wonderful presentation as well. It captures my interest both right now and long term. So I have questions regarding your approach and some other things that I've seen in literature regarding how we can achieve autonomy, robot autonomy. Reinforcement learning works with the presumption that you can define a policy that is robust enough to represent real world. And I see some limitations to it, to the fact that it's similar to classical programming. You can't create a classical program that would do things intelligently, right? You have to think of all the use cases. So when you're creating a policy, you have to create a policy that assumes or works with the best outcome. Literally, you're defining what the outcome is, be it standing up uprightly or walking without falling in the simulator. Now, my question is, what other alternatives to reinforcement learning that is firstly scalable, achievable as well, do you see in this field of autonomy? There are people are taking approaches to visual VLMs to test the theory of or to see if they can understand the scene. Some researchers disagree with that, and therefore you have works like JEPA, joint embeddings from Yan LeCun at NYU, another institution. So, what other competing approaches do you know of, or do you see that we can achieve autonomy? And now, not just autonomy in simulators, because we have seen two real problems. Autonomy in real world, right, where we can confidently say that, okay, in so time, if we overcome these challenges, we'll have robots as ubiquitous as we have smartphones.
Yeah, that's a very good question. First thing I want to tell you is that's a question that would require 5 years of PhD to answer. Because if we figured it out by then, if we had it figured out, we wouldn't all be working on this research. So like what you're asking is like, what you're asking now is what everyone is trying to figure out right now. So that's going to be tough for me to answer. I would say that your view of RL is not perfect. You didn't, what you thought were the limitations is not actually the limitations. The first problem is if you have a good enough limitation, if you have a good enough simulation, like if realistic physics simulation of your problem, you are going to run into the same problems that you would run into. That's not a good explanation. Okay, so in reinforcement learning, we have something called out of distribution. And so out of distribution would exist when your simulation might not have all the conditions that it would in real life. So you're not actually going to, you're learning the policy, you're not actually hard coding the policy, right? Now, what LLMs come in, we have this new field of research called foundational models. So these foundational models are like LLMs or LLVMs where like, because they've kind of learned the world, they can generalize better than RL algorithms. However, everyone is soon realizing that it's not all, what's the term, rainbows and roses as we thought it was. And we're all like, okay, no, we have to go back to reinforcement learning to figure reinforcement learning out. So no, I don't know what the alternative will be in the next 3 years. It might change. Some random MIT professor might figure out a new technique. But I would tell you that whatever it is, it would be based around RL. Because even the foundational models that you're talking about are done by RL researchers and RL framework. Even ChatGPT works with reinforcement learning. The way they make sure that the model answers your question is by adding a reward function to, okay, if you successfully answer this question, then you get a reward. So it's actually also trained with RL. So RL, I believe strongly is the future. I hope it is, because I'm spending 5 years studying it. And if it's not, I'm screwed. But yeah, I think RL is the future. It might not just be the exact flavor that we're doing now. It might be something new. It might be a blend of some other field or reasoning from computation. So I'm sorry I didn't really answer your question. My point is everyone's trying to figure that out now. So yeah, we don't know.
All right. Yeah, so thank you. Because of our limited time, I'm going to take maybe maximum of 2 more questions. I will go to the chat section, which says, that's from Samuel Oyefusi. You might as well follow. It says, in your own experience, what's the most reliable approach to SLAM, especially when dealing with ODOM to base link transformations? Have you tried fusing LiDAR and camera data for mapping? And what worked, what didn't work? Also, how do you use reinforcement learning for improving SLAM performance, especially when training data or limited or noisy ones? So maybe the second part of the question might be what you want to answer well.
I mean, second part of the question is really complex, but unless I'm overthinking it, the question. But to tackle the first question, I will tell you that unfortunately, there's no single solution to the SLAM problem. There's no one SLAM algorithm that solves everything. It depends on your problem. If you're indoor, use a different SLAM algorithm. If you're outdoor, use a different SLAM algorithm. If your cameras are really fast, as opposed to, sorry, not your cameras, rather. If your robot is really fast, as opposed to a robot moving slow, you have to use a different SLAM algorithm. If you want to use like visual renderings and your robot is really fast, you're going to have blurs. And so you might not be able to capture visual odometry. And so you might need to use what do they call them? Visual IO algorithm, which is you have a camera, but you also have an odometry. Is that what it's called? Odometer, whatever. So I wouldn't say that
inertial.
Yeah, visual inertial odometry. So I wouldn't say there's one approach to, there's no one single approach to SLAM. So what we usually do in our lab, or there's actually a lab close to us called the ARIA lab, this is actually like what they do, perception and whatever, is like the company would send over their requirements. They'll go over the requirements and they now, pick the SLAM algorithm that they wish to use. So when dealing with ODOM to base link transformations, I do not, as of right now, I do not actually write any ROS code. I just supervise. So if you're asking me about the low level stuff like dealing with ODOM and base link transformations, I don't really know what that is. Have I tried fusing LiDAR and camera data for mapping? LiDARs are very computationally expensive. So are cameras. I wouldn't imagine doing both of them at the same time. I would believe some companies do that. but it's a lot of computational power. LiDARs themselves produce really accurate mapping systems. Cameras themselves also produce accurate mapping systems. Although LiDARs are better in some cases as opposed to camera, but you typically just stick to one, and then you can have some kind of sensor fusion in between that. What worked and what didn't work, and what would you recommend?
So,
Yes, like I said, there's no system for that.
Oh, all right. Thank you so much. By the way, I just need to point out that for those of you who ask questions for the first speaker, I really appreciate you, Teja, for doing the great work. She's also trying to make sure that she answers all the questions on the chat. So if you feel like you asked a question and it was not answered, check the chat section and you will see that she has probably answered them there. All right, thank you so much. Thank you, Mr. Oseni, as well. We really appreciate this.
I don't want to say, feel free to text me on LinkedIn. A lot of people message me all the time. Right now, like I said, and I just woke up and I was in the lab all night, so I'm still very sleepy and slow.
Yeah. So for those of you who noticed that it was actually yawning when he came on, I saw it. It was yawning. So the time difference is something there. He was just coming from a lab, and I think it's in the very, very early morning over there. So he's been busy. So that's why you saw him. He was trying to hide the yawning. I saw it. Yeah, but he has been stressed. So thank you so much for honoring this visit. By the way, this video or this meeting is going to be made public on YouTube. So we'll share the link to everyone in our community, and then you can also go over everything we've done again. And I think some people ask if they can get your slides. I told them that we don't have that permission yet. So is it possible to get your slides?
I need to ask my advisor. So if I have permission, I'll ask you guys, because it's on my lab slides and stuff. So, but I'll ask permission, and you probably say yes.
Okay, so we can. Okay, all right. So no problem. We'll let you know whenever we decide. I would have loved to take Kenneth's question, but I'm sorry, Kenneth. The time is almost up, and we have to do other things. So the other thing now is, I guess it's like AOB or something. So as a community, this time around, let's just feel free to. Oh, by the way, while we are talking, Tosin might actually answer your question in the chat section. Oh, I think that's a good one.
Yeah.
So you can answer his question in the chat section. So again, let's freely talk this time around. We have like maybe 10 minutes. Let's freely talk. If there's something particular you want to talk about the community, about ROS in Nigeria, all those kind of questions. The questions not related to what the two speakers just did today. Just questions on ROS in Nigeria, the community, how we can make it better. What's your suggestion? I know some people were saying we should have like competitions, things like that. I don't know. So if you want to say something about that, just please kindly raise your hand and let's hear you out. It's going to be recorded actually. So anybody saying anything? Okay, Bello, is Bello's hand still up? Bello Ayotunde. Oh, is that Usman? So I think Usman, you can go ahead, please.
Hi, good afternoon, everyone. Beautiful session.
Yeah.
I really appreciate the speakers and the organizers of this. So ROS Nigeria, as we know, most of the physical meetings have been in Lagos, and we have people all over the country. So, and I've met
sorry, we are having where the echo is coming from. Sorry, Abdullah, can you mute? Yeah, thank you. Okay, I think Abdullah is muted. You can go ahead now. Let's see if there was still
okay. So I was thinking of the possibility of having like smaller hubs, people in other states where they could come together and meet. and maybe try out a few things themselves. I'm sure that would also help improve, build the community, and we get to learn more and share more stuff among each other. Personally, I'm in Abuja, and I've met Samuel Eliaga in Abuja here. In fact, we went to the same university, so I knew him from those days. And I think speaking with him, we are really looking forward to having something like that where we can get to know those members of the community that are over here in Abuja and maybe meet up 1 or 2 times. And probably during the next ROS meetup, we're hoping that we could actually all attend from the same place where we just maybe get a space where we just come together and we attend it. Though it's going to be virtually, we want to attend it together, and I think that would help in building the community.
Wow, that is awesome. By the way, Usman has been very, very supportive of this community from day one, and I really appreciate him for that. Even though he's not in Lagos, actually, he's in Abuja, and he has always been, supportive of what we are doing. So thank you. And again, there was a time I discussed with some of the guys in Abuja that it's like Abuja ROS people are growing, and I think you guys should start holding your own meetups and things like that. And I'm really glad because I think Samuel shared this with me that you planned, having a kind of something like this also, and but maybe 1 or 2 reasons you couldn't hold it. Yeah, so if anybody is here, you are in Abuja, please reach out to these guys. They might be having a ROS meetup maybe in a couple of months now. So please reach out to them. And yeah, they are also on our Slack channel. You can also reach out on our Slack channel. So thank you for that. Again, if you feel like there are roboticists in your own area, it might not be Abuja, it can be in another state, maybe in Port Harcourt, wherever you are. If you feel like you're having a growing number of ROS people or robotics people, you might want to, start a meetup like this. And interestingly, the open robotics, they see what we are doing and, they appreciate what we are doing as well. Let me also mention that, we got 3 last year. It was just 2 of us from Nigeria. Look at it this year now. At least I can count 3 people that got the ROS Diversity Scholarship from Nigeria. So it's more like as if, the number is growing. Last year it was just, 2 guys. Now we have a female with 2 guys as well. And it looks like we are getting something positive from them. So please, if you want to go in all for us, go in all for us. Yeah, thank you so much, Usman. Is there anybody? Okay, I think I have Abdullah, right?
Yeah, sorry.
Okay.
Sorry, Salah.
Go ahead, please.
Yeah, this is Ayo. Good afternoon, everyone. So
yeah,
just on the topic about like what we can do to make the whole programming space a lot more accessible. So I believe the biggest problem. Like we face right now in Nigeria in terms of like just generally technology, even in terms of like basic developments, is knowledge. So what I mean is we don't have industries to start with. So like our universities basically don't teach this type